Today's topic covers 4 points: option, duplicate letters, and modules. I also want to add more physics to the code. Let's see what the duplicate letters problem is. The code in purple is the algorithm for collecting the letters into the target word. This algorithm only checks at the start of the letter list. That's why the target letter is skipped if it is not at the beginning of the list. The second issue I am dealing with is the option type. Do we really need the option type here? Suppose the computer operates on some data and produces some result. For example, the computer is doing division. The result takes different values. Sometimes the result does not make any sense, which might cause problems with the computer's performance. There is a need to handle this situation in order to avoid potential problems. One way is to collect the values of the operations which make sense, and tag the illegal operations with a different value, such as none. Let's take a look at an example from the Rustlang website. This function performs the operation of division and returns an option type. When y is 0, the function returns none, otherwise it returns the values wrapped in sum. Now we have the problem of how to use this option type after we get the result. One way to use the result is to match against the option and unpack the option value. The inner value is unpacked for use. Alternatively, we can use if-let for pattern matching and destructuring. Finally, one thing I want to mention: this code does not crash the application. For more information about the if-let pattern matching, check this website. In our current application, every food object carries a letter. The operation collision always returns a letter. We will change the type of the letter field from option to char, like this. For the option type variable, unwrap either returns the inner element or panics when it receives a none. Now we don't need them. Let's check the code and remove the wrapping with sum. To resolve the duplicate letters problem, we have rewritten this method and rename it as findFood. This method returns the index of the food object wrapped with sum or none if no collision occurs. The loop block calculates the distance between the worm and each food object. Please pause the video to read the code. Accordingly, we need to modify the code here. We can merge the nested if blocks into one block. We move the worm, bounce the worm if necessary, and check for collisions. The variable found may be sum or none. To be explicit, this is the type of found. If we have found something, we unwrap the index. Then check if the letter is the desired one. If it is, the worm grows. If the food object is not the first element, swap it with the first one. Then we remove the first element. In case you forget the target word, play the audio if the P key is pressed. If all letters are collected, reset the game. Now compile and run the code. Bat. Next, we are going to learn the basics of Rust modules. By example, we will create a Rust project called worm2 and add dependencies. This is the final cargo.toml file. Let's open the src folder. There are 7 files inside. We can view the organization of the files in a tree view. As the project grows, it's better to organize the code logically. Rust modules help organize a program into logical units for improved readability. A module can include functions, structs, traits, impl blocks, and other modules. Rust code can be split into multiple .rs files, with each file serving as a module. To include a file in the module tree, we need to declare it as a submodule using the mod keyword. This declaration takes place in a parent Rust file, which can be main.rs for applications, librs for a library, or mod.rs for submodules. Currently, I have placed the module declaration in the main.rs file. We need some audio files for the sounds. You can download the audio files here. Now, let's first take a look at the main function. Here are the module declarations. Game is the struct that we need to feed into the eFrame run native function. In our previous examples, we used my app and my game. No matter what the name is, this is the struct we need to implement the eFrame app trait for. Now, let's turn our attention to the consts.rs file. We have seen the enum definition. We have also seen the constant zooanimals. We add the keyword pub here to make this constant visible to the code in other modules. More constants are defined here. KS is the spring constant for simulating the pulling on each body unit. Let's examine the head.rs file. For more physics, we add a field named force. The default value for force is 0. Here, we introduce Newton's second law for the motion of the head. These are the components of the velocity along the x and y axes. The acceleration, namely, the change of the velocity, is calculated based on the second Newton's law. We update the speed field. Finally, we update the position of the head. The paint method is basically the same as before. The unit.rs contains the definition of the unit struct, which is nothing but the struct body renamed as unit. There are no big modifications to the tick method. We use deform instead of force to reflect the fact that here Hooke's law is employed. This is the paint method. The definition of the struct worm is almost the same as before, except we made the struct and its fields visible to other modules. We have the same bounce and grow methods. We have already talked about the food struct. We only changed the type of the field letter and made the struct and its fields public. The game.rs file is the organizer of the game. These are the use declarations, on which I will spend some time later. The struct is public now, but the fields are all private. The reason for making the struct public is that the main.rs uses the struct. This is the create food method. These are the find food and play audio methods. This is the startup UI method. This is the implementation of the eFrame app trait for the game struct. Here, we don't control the speed of the head, we apply a force to the head. The remaining code of the game.rs remains the same, except for minor modifications. I have already uploaded the source code here. Finally, I want to talk about the use declaration. A use declaration creates local name bindings that are synonymous with another path. This is typically used to shorten the path needed to refer to a module item. For example, without the use declaration, we access the struct game like this. With the use declaration, we can directly use the struct game. Similarly, in the head.rs file, if we change the use declaration like this, we have to use the new bindings accordingly. Finally, compile and run the program. Thanks for watching.